Hello and welcome everyone to the second virtual training module hosted by the Sustainable Materials Management and Extreme Events Reconnaissance Organization. This training module will focus on post-disaster waste materials estimation integrating FEMA's HAZUS-MH software. My name is Dr. Derek Mannheim and I'm a researcher within the SUMMEER organization who will be leading this training module today. I've prepared a brief presentation and two in-depth case study tutorials to walk you through the basic steps of applying HAZUS-MH to make reliable predictions of post-disaster waste materials, quantity, and composition. These initial estimates are necessary to comprehend and fully explore the efficacy of various sustainable management and treatment options for post-disaster waste materials following a catastrophic disaster event. As introduced in the first virtual training module, a major contribution of the SUMMEER organization is the preparation of virtual assessment reports that summarize the key findings related to the current management of post-disaster waste materials in the wake of a catastrophic natural disaster event. Within each of these virtual assessment reports, formal estimation and reporting in the material quantity and composition is necessary to provide a quantitative understanding of the amount and types of waste generated after a natural disaster. This data provides baseline understanding of the sustainable waste management options that can be implemented and allows a direct comparison to field reported data. As with any modeling tool, there is inherent uncertainty to address with the modeling predictions. Effectively characterizing this uncertainty requires a combination of predictive approaches, such as the use of iWaste and HAZUS-MH, to arrive at a range in waste material characterization estimates. As a brief review, iWaste is an easy-to-implement modeling tool for generating order of magnitude, emphasizing approximate weight, volume, and composition estimates of post-disaster waste materials following a natural disaster. HAZUS-MH, which is the focus of this training module, is a more complex and powerful state-of-the-art risk assessment software program developed and maintained by FEMA for analyzing losses from floods, hurricanes, earthquakes, and tsunamis. Together, these tools can provide lower and upper predictive certainty bounds for the debris characteristics following a natural disaster, including, for example, the weight, composition, and spatial location. This training module presents a standardized framework for post-disaster waste materials estimation, integrating FEMA's HAZUS-MH software. The intended audience of this training module is for new members participating in virtual assessment report activities that need to get up to speed with using available debris estimation software, and for the greater research community. After viewing this module, you will gain new experience with the capabilities that HAZUS-MH offers, along with a general understanding and awareness of how to best generate, analyze, and post-process results using HAZUS with a specific emphasis on the development and publication of future virtual assessment reports. And now I will present a brief introduction to HAZUS-MH. HAZUS-MH is a powerful, state-of-the-art risk assessment software program developed and maintained by FEMA for analyzing potential losses from floods, hurricanes, earthquakes, and tsunamis. It has the capability of estimating both direct and indirect physical, economic, and social impacts resulting from a disaster event of interest. HAZUS-MH currently integrates ArcGIS to produce spatial estimates of potential losses from a variety of infrastructure, including residential communities, commercial enterprises, and industrial facilities. Predictions from HAZUS-MH can be applied both during disaster planning or during the response and recovery phases to assist in local to state level risk analysis, loss estimates, and post-disaster materials management applications. HAZUS-MH relies on a nationwide inventory of social and infrastructural data that can be aggregated on various analysis levels, starting at the state level, more coarse analysis, and progressing down to the census block level, the finest detail. These inventories include both attribute information, in other words, distinguishing features used to classify data, as well as geographical information, in other words, location, area, extent, etc. The HAZUS inventory data can be dissected first into site-specific data and then aggregated data components. Site-specific data includes essential facilities such as hospitals, schools, police stations, and medical facilities, as well as high potential loss facilities such as airports, ports, wastewater treatment facilities, and solid waste landfills. Site-specific data also includes road network infrastructure and utilities such as power plants. When building a study region, users are also encouraged to update this inventory to better reflect the site-specific infrastructure affected by the natural disaster event. Aggregated data includes the general building stock, demographic data, as well as vehicle and agricultural data. The general building stock in HAZUS-MH includes all residential, commercial, and industrial infrastructure in a given region of interest. This data is classified by material type and occupancy class. The general building material types are first aggregated into 5 primary categories, including wood, steel, concrete, manufactured housing, and masonry. The specific material types can be expanded into 36 distinct categories, as summarized in the table presented in the middle of the slide. In addition, approximately 33 occupancy classes have been defined in HAZUS and are shown in the table to the right. The majority of the occupancy classes are of commercial classification, ranging from parking lots, movie theaters, hospitals, and offices. Residential occupancy classes vary from single-family to multifamily homes, temporary lodging, and mobile home communities. Industrial facilities are primarily classified based on product types generated from these facilities. In other words, food, metals, or high technology. As mentioned previously, HAZUS-MH is a disaster-specific tool that can be tailored to simulate any disaster event ranging from earthquake, flood, hurricane, or tsunami. It is programmed to make reliable estimates of potential losses based on the unique physical or meteorological characteristics of the disaster event. As output from the HAZUS-MH simulations, direct damage to the building infrastructure and economic or social losses are computed. Induced damage, which is the focus of this training module, includes the spatial estimation of debris generation, which can be achieved from the earthquake, flood, and hurricane simulation frameworks only. Examples of direct losses may include the cost of building repair, income losses, agricultural damages, human casualties, shelter and/or evacuation needs, as well as average annualized loss values. Importantly, HAZUS can be run and analyzed using various levels of sophistication. The Level 1 analysis includes baseline simulations that generate loss estimates using the data compiled on the national inventory datasets with few modifications to these inventory estimates or model parameters. More advanced level of analysis, for example levels 2 and 3 as shown in the figure, may consider updating the inventory estimates and consider the use of detailed engineering data to represent losses from certain facilities of interest. In the interest of SUMMEER's applications, a baseline Level 1 analysis is generally sufficient for providing reliable estimates of debris generation following a significant natural disaster. This slide summarizes the main framework for performing a reliable HAZUS-MH simulation. The first step is to properly identify, select, and set up the study region in HAZUS. Preliminary virtual reconnaissance efforts can be performed to help constrain the simulations to only analyze the disaster-affected region of interest. This may include identifying regions that have declared a federal state of emergency or that have reported substantial damages and losses. This preliminary step will assist in narrowing down the scope of the loss simulation and will greatly reduce the computational effort and simulation time required by HAZUS. Once the region has been identified, the inventory data for this region will be loaded into HAZUS prior to performing the simulation. The second step is to specify the natural hazard characteristics, which includes defining what type of disaster event you are simulating, whether the hazard will be simulated using historic, probabilistic, or user-defined data. Historic disaster event-specific data have been previously loaded and stored in HAZUS, whereas probabilistic modes of disaster specification randomly generate disaster event characteristics. Usually, you will select the user-defined option when specifying the natural hazard characteristics. A third step is to simulate the impacts of the natural hazard event using HAZUS. After the study region and natural hazard characteristics are defined and loaded, disaster-specific damage and loss functions are applied within HAZUS-MH to generate an estimate of the spatial distribution of post-disaster waste materials. Generally, the parameters defining the damage and loss functions do not need to be updated for development of the virtual assessment reports. But users are able to access, view, and modify these functions to produce more reliable estimates of the spatial distribution of debris and waste materials. Finally, the fourth step is to perform an engineering assessment and interpretation of the results obtained. This involves some understanding of the location and characteristics of the general building stock, essential facilities, and transportation or utility systems within the disaster-affected region, and how you would expect these structures to respond to the unique characteristics of the disaster event. For example, do spatial estimates of debris quantity or composition align with the disaster path and intensity? This step generally involves some amount of reflection and questioning on whether the model estimates are reliable given the attributes of the disaster event and the affected region. Now I'll briefly review how HAZUS-MH generates estimates of disaster debris quantity and composition. First, starting off with flooding simulations. I believe this information is very important to help the user become more familiar with the modeling approach behind HAZUS simulations specific to debris estimation. For each building occupancy class within HAZUS, there is an empirical flood depth damage curve used to estimate the percent damage of a structure. Given the water depth predicted within HAZUS-MH, the percent damage for each structure within the census block of interest is computed. If the percent damage threshold exceeds 50%, total loss of the structure is assumed, and the debris weight or square foot estimates for the 8-foot plus row presented in the table on the slide are used to calculate the total debris generated. Note that in this table here, both structural and non-structural debris estimates are generated in the event of a complete loss. However, if the percent damage is below the threshold of 50%, the debris tonnage is based on the flooding depth and does not take into account damages to the structure or foundations. In other words, only finishes are included in the estimates. Therefore, debris tonnage estimates for a given census block are mainly based on the building occupancy class, square footage per occupancy class, and flooding depth in the affected region. Now, for hurricane simulations, the approach to estimate debris is somewhat different than that presented for flooding in the previous slide. First, cumulative probability density curves are developed to represent, in the event of a hurricane event, the probability of damage occurring given the peak gust wind speed encountered and the damaged state of the affected building, ranging from minor, moderate, severe to destruction. The quantity of debris generated is then estimated from the damage intensity function, given the building material type, peak gust wind speed, and the surface roughness of the affected region, ranging from open, meaning rural areas, to trees, indicating a dense forest. Both the probability of damage and the damage intensity obtained from these empirical curves are then multiplied together and by the square footage of the building material type within a given census block to arrive at a total estimate of the debris quantity generated. A building material type specific debris distribution matrix is then applied to apportion this total debris generation estimate into brick wood, steel concrete, or vegetative debris categories. Therefore, debris tonnage estimates for a given census block are mainly based on the peak gust wind speed, building material type, square footage per material type, damage state, and surface roughness of the affected region. The figure on the right below is an example of a damage intensity function for a wooden building type, single-family home occupancy class. As mentioned above, the debris generation is a function of the peak gust wind speed and simulated in the census block on the x-axis and the surface roughness, as indicated by the different colored curves. For this particular structure type and occupancy class, the debris generated is largest for the open rural area, moderate for the urban areas, and smallest for the heavily wooded rural area. This is because an open rural area has low surface roughness, which intensifies the near-surface turbulence intensity, thereby magnifying the damage impacts of a wind-based event. The figure on the left below is an example of a cumulative probability density curve for the same building type occupancy class shown on the right. Notice that for a given peak gust wind speed, as the damage state increases from minor to complete destruction, the probability of the damage occurring decreases. This result is based on empirical evidence from many field observations that completely destroyed buildings are a less representative damage state on a statistical basis of the overall population of affected buildings in a disaster-affected region. I will now go through the steps required to set up and run your own HAZUS-MH simulation. The focus of this training module will be on flooding and hurricane disaster events, which are the most probable events you'll be simulating in the development of the virtual assessment reports. You will first need to download and install HAZUS-MH version 6.0 from the FEMA download page. I have included the link to this download page in the presentation here for your reference. Under this link, you will also find the state-specific inventory datasets required to run HAZUS-MH simulations. The download and installation requirements include a Windows operating system, version 10 or higher, 64-bit, along with access to ArcMap version 10.8.2 with the Spatial Analyst extension included. To run ArcMap, you'll need a standalone or community license to access ArcGIS, which is usually available for most academic or governmental research institutions. In addition, since the computational requirements for HAZUS are quite demanding, please also make sure that you have a reliable operating system in place, which includes a 2.4 GHz processor speed, 8 GB of RAM, and 100 GB of available disk space. Prior to installing HAZUS, please be sure that these requirements are met, otherwise you will encounter some difficulties in the download process. You can follow the specific download and installation steps available from FEMA under their YouTube channel page, which also reviews how to download and install the state-specific databases required to run HAZUS-MH simulations for your disaster-affected region of interest. Once you have successfully installed and opened HAZUS-MH, you will now be able to build a new study region. Click on the HAZUS-MH icon created on your desktop, and you will see the following startup dialog box as shown on the left of the slide here. Make sure to select Create a New Region, click OK, and enter in the name and description of your study region. Note that once you have created a new region, you can also open, delete, duplicate, export or backup, or import a region to facilitate HAZUS utilization among multiple users within the SUMMEER organization. I will now review the general steps for setting up and running a flooding simulation in HAZUS-MH. After creating a new study region, or name and description, you will be prompted to select the disaster type. In this case, please select the flood checkbox. In the case of a hurricane, which I will cover next, please select the hurricane checkbox. When you select next, a new dialog box will pop up prompting you to use the hurricane scenario wizard. When this occurs, please make sure to select no, as we will set up the characteristics of the hurricane event later on. Now, the next step will be to select the desired activation level. For both floods and hurricanes, I recommend that you choose by county and identify from preliminary research which counties have actually been affected to some extent by this disaster. This will help place geographical constraints on the HAZUS-MH simulations and will reduce the computational effort and runtime of HAZUS to produce a reliable result. In some cases, it may also be easier to aggregate by watershed or census tract if more detailed simulation results are desired. Next, you will need to select the correct state and counties. When choosing the counties that are affected, make sure that you hold the control button down to keep the counties of interest highlighted in blue, which means that they will be selected for further analysis and simulation. You can now hit the Finish button and the new study region will be created. Depending on the size of the disaster-affected area, this will take some time to run, maybe up to 10 to 20 or 30 minutes. Once HAZUS has set up your study region, you will see the following dialog box in the bottom right corner that the region aggregation was in fact successful. Now that you have successfully built your study region, you can now open the region by first selecting Open a Region in the HAZUS Startup box, and then selecting the region in the Open Region dialog box. Note that the date of creation, description, and title are displayed neatly in this summary box. This is a helpful information when there are multiple study regions that you will need to select to perform a given simulation. We will now walk through the steps required to set up and run a successful flooding simulation in HAZUS. This will require 5 individual steps, including selecting the flood hazard type, importing the digital elevation model, developing the stream network, creating and defining a new flood scenario, and performing the hydrologic and floodplain analysis. First, we will specify the flood hazard type. In the ArcGIS menu options, please select Hazard and then Flood Hazard Type. In this simulation, we are dealing with the Michigan flooding event, so we are only dealing with riverine flooding. In other flooding events located close to the coast, both riverine and coastal flooding options may need to be selected. Next, we will need to import the digital elevation model, or DEM for short. Again, select the hazard menu, then select user data. This is where the details of the DEM must be specified in this dialog box. In some situations, you might have flood depth already given to you or available as a FIT, depth grid, or a HECRAS file. In these cases, you can skip most of the following steps and simply import the flood depth grid directly into HAZUS-MH. What follows is a complete description of setting up and running a flooding scenario in HAZUS-MH from scratch. Now, to obtain the DEM, you'll need to select the Determine Required DEM Extent option in the dialog box. This will bring up the DEM bounding coordinates in decimal degrees. If you know the spatial extent of the disaster-affected region, you will need to specify the coordinates of the bounding box around your region. You can first do this using Google Earth or creating a rectangle around your region in ArcMap. Once you enter in the coordinates, the correct DEM files will auto-populate in the table below as seen here. Select the Download and Unzip All option, which brings up the DEM for your region of interest from the USGS catalog. Also note that usually the 1 arc-second resolution is the best option to choose. The results of your DEM import should look like the following after you have successfully imported it into your study region. Note that the red indicates areas of high elevation and green indicates areas of low-lying elevations. Okay, so the next item to accomplish will be the development of the stream network. Again, select the hazard menu and select Develop Stream Network. I would recommend using a smaller input stream drainage area of approximately 1 kilometer squared, corresponding to 0.386 square miles, which provides generally a good trade-off between the computational effort and model resolution and reliability. The stream network will then be generated after some time. This is typically one of the longest steps, and the runtime dialog box will complete after a successful build. You can now see the individual stream reaches highlighted in blue superimposed over the study area based on this analysis. Notice that the reaches occur in the low-lying areas of the watershed as expected initially. We are now ready to set up and run a new flood scenario. Again, select Hazard menu and hit Scenario and select New. Please be sure to enter a proper name and description to identify this particular scenario. Then select river reaches that you would like to actually model in your scenario by clicking the plus button and dragging the cursor over the stream network you would like to include, which then turns the color from dark blue to light blue to indicate that they are in fact selected. Oftentimes, the stream network build will include undesired stream reaches that were not affected by the disaster event, so you can further refine in this step which actual stream segments or reaches are pertinent to your simulation. After you have finished selecting and refining your reaches, hit the Save Selection and then OK to move on to the next step. After you perform this step, the model stream reaches will now show in red, indicating that they are in fact selected and chosen, instead of light blue as shown in this figure. You are now ready to perform the hydrologic analysis. Again, select the hazard menu, then hit Riverine and select Hydrology. Select Yes to ensure raster processing. You will see a processing bar now to indicate that the hydrology is now being modeled. After a successful run, the dialog box will show up and you can select OK to continue. As observed on this slide here, note that not much changes on the HAZUS display screen are observed after the hydrologic analysis operation has been performed. The final step involved will be to delineate the floodplain. Again, select Hazard menu, then hit Riverine and select Delineate Floodplain. The Riverine hydraulic analysis will show up, indicating first the analysis type. You have the option to select a series of return periods, for example, 10-year, 100-year, or 500-year events to represent a flooding scenario from storm events of various probabilities. Note that as the return period increases, the probability of the flooding event occurring decreases, but the damage incurred increases substantially. To make the HAZUS-MH simulations more realistic, I suggest that you select the single discharge option instead of a single or multiple return period, and specify the volumetric discharge manually in cubic feet per second. You can access and obtain actual stream gauge data from USGS online, from the stream networks in your model, and use these estimates to run a more realistic flooding simulation. From my experience, if you do not select this option and do the bit of extra research to find peak discharge measurements, the damage estimates will be much less severe, significantly different than potential field observations. After specifying these options, don't worry about the roughness coefficients here. The processing status dialog box will appear and the runtime dialog box will come up immediately after the floodplain has been delineated successfully. Now the extent of the floodplain will be shown in HAZUS as an orange bounding box. You can zoom in and check the flood depth grid that has been created and superimposed on the digital elevation model in HAZUS. Note that the high and low flood depth values are defined by dark blue and light blue shading respectively. Double check that these values are reasonable and in fact consistent or slightly elevated compared to existing flood depth maps within the region of interest. Congratulations, you are now ready to run the damage and loss assessment in HAZUS for a flooding event. Let's now look into how to set up and run a hurricane event within HAZUS-MH. After building and opening your study region of interest, you are now ready to set up and import the necessary files required to run the hurricane simulation. For this tutorial, we will focus on the HURAVAC storm advisory data, which is generally the most reliable data source for the hurricane storm track and intensity. Again, select the hazard menu and hit Scenario. This will bring up the Hurricane Scenario Management wizard. Click Next, and you will see the Scenario Operation dialog box. Here you will select Create New Scenario and Activate. This will now bring up the User-Defined Scenario Type dialog box. Now, select Import HURAVAC Storm Advisory option, click Next, and you'll run into the storm selection page in the Scenario Wizard. Under the Storm Selection dialog box, please select Atlantic or Central Pacific, depending on the location of interest, and scroll through the historical list to find your hurricane of interest. If you are having trouble finding your hurricane, you can filter each column either by alphabetical order or by year to help locate your hurricane of interest. After you have located, highlighted, and selected your hurricane, hit Next, then hit the Download Selection button. This will bring up the Edit Storm Track dialog box as shown here, where you can double check the storm track, wind speed, pressure, and radius type. Oftentimes, the hurricane data contains some or a few errors that should be verified with the HURAVAC database prior to running a full simulation in HAZUS. If everything appears correct, please select the Next button. The wind field model will then run and bring up the Storm Track Data Review dialog box, which summarizes the model predictions for your region of interest. You can now review and validate the hurricane track predictions. If everything looks okay, select the Next button and move on. After hitting the Next button, the Scenario Review dialog box will appear as shown here, where you can review the maximum wind speed and file information. Hit Next to enter the Activate Scenario page and click Yes. Make the scenario active. Again, after hitting Next, you're ready to run the damage and loss assessment in HAZUS for a hurricane event. Congratulations. Now we are ready to run the HAZUS-MH damage and loss assessment. For both a flooding and hurricane event, under the Analysis tab, you can first check the damage functions used to generate debris quantity and composition estimates. Then you can select the Run option. Under the Analysis Options dialog box, you can select which infrastructure or analyses should be included in your simulation. I would suggest hitting Select All so that you can review all of the data generated from a complete damage and loss assessment performed in HAZUS-MH. After selecting OK, the Processing Status dialog box will appear. This step takes quite a bit of time, so go fill up your coffee mug or make some lunch. The Flood Analysis dialog box will then appear to let you know that the simulation has been successfully run. Click OK to proceed to viewing the results. Alright, so one of the most important results you'll obtain from the HAZUS-MH simulations for SUMMEER purposes is an estimate of the spatial variation in waste material estimation results. In HAZUS-MH, you can actually plot debris tonnages as a function of census block and color code these values by intensity. Here I am showing the results of the Midland, Michigan flooding event, where the debris tonnages for the cities of Midland and Saginaw are mapped. In both plots, cooler and warmer colors indicate lower and higher debris quantities, respectively. In both cities, most of the highest material quantities are located in the dense, urban, low-lying areas next to the rivers most affected by this flooding event, as indicated by the red and orange areas overlying the smaller census blocks. In addition to total debris estimates, you can also separate and analyze the spatial variation in debris composition in HAZUS-MH. As an example, shown here is the spatial variation in debris generated from HAZUS-MH for Hurricane Laura, for both brick and wood on the left and vegetative debris on the right, individual categories. For hurricane simulations, vegetative debris categories, in other words trees, can be selected and viewed in HAZUS along with the concrete, steel, and brick and wood categories. The path of Hurricane Laura is also superimposed on both plots. As you can see, the color code of the path signifies the hurricane intensity on the Saffir-Simpson scale, where green and yellow colors indicate Category 1 and Category 4, respectively. Again, in both of these plots, cooler and warmer colors indicate lower and higher debris quantities, respectively. Note that the hurricane was of highest intensity when it was approximately a quarter of the way inland in the state of Louisiana. Also note that the locations with high infrastructural debris generation are not correlated well with locations of high vegetative debris. This is as expected given urban areas generally have low amounts of vegetation present as compared to rural areas. The results shown on previous slides are important graphical approaches to observe the extent and location of damage and waste materials generated after a disaster event. To access the actual debris tonnage quantities, there are a few options you can select to export your data from HAZUS-MH. First and foremost, you can download and install the HAZUS export tool available from FEMA and ArcGIS. This tool will automatically generate an Excel spreadsheet populated with all the data you need to conduct the virtual assessment report. You also have the option to view the results under the Results tab and copy and paste this data from HAZUS-MH directly into Excel. I think this is the easiest and most convenient option in my opinion. Lastly, if you're dealing with a significant amount of data, you can access the results through the SQL server in HAZUS using Microsoft HAZUS-MH. This is a more advanced option to access the results, but it is much easier to find what you need and download large quantities of data files. There are YouTube videos available from FEMA that can assist with setting up both the HAZUS export and SQL server so that you can readily access and download the data generated from HAZUS. Similar to the IOA simulations performed in tutorial number 1, it is always good practice to interpret and deliberately question your simulation results from HAZUS-MH. The best way to go about this interpretation step is to compare the disaster-specific characteristics with the debris generation results. If you overlay the disaster characteristics with your debris generation map, as shown here for the Midland flooding event and for Hurricane Laura, you should see a qualitative correlation between the two. In other words, dense urban areas with higher flooding depths or hurricane intensity should be associated with higher debris tonnages. As observed for Hurricane Laura, counties in the direct path of the hurricane under a Category 4 classification, the highest intensity, correspond to the largest quantity of debris and concrete and steel debris. You can also plot the disaster characteristics such as peak wind speed or flooding depth per census block or tract against debris generation estimates to verify that there is some correlation between the two. Now, after exporting your data from HAZUS-MH, you can apply further post-processing and construct additional figures to further interpret and analyze your findings. Here I have plotted the total number of affected buildings for the Midland and Saginaw areas and color-coded each bar by the damage percentage level. This figure shows that the Saginaw region had a higher number of affected buildings than the Midland region, particularly buildings associated with moderate damage below the 50% threshold as discussed earlier. Very few buildings were associated with complete destruction or total loss, and a fair share of the buildings were either unaffected or sustained flooding damage below 10%. In the second figure, I've also separated this analysis into the main building material types for each region. Masonry buildings were generally most affected in the 11 to 40% damage classes for both regions, whereas manufactured housing was most affected above the 70% damage class. In addition, wood buildings shared in some proportion of the total number of affected buildings for each damage class, particularly for the Saginaw region at higher damage levels. These are some examples of how you might consider portraying your results and are in no way mandatory. However, they provide additional opportunities to analyze and present your results in the virtual assessment reports. Now I'll walk through a case study tutorial using the Midland, Michigan flooding event as an example of application of HAZUS-MH. This event was caused by historic rainfall in the central Michigan region, which was exacerbated by a succession of dam failures and breaches, resulting in catastrophic inundation and damage of both urban and rural areas located downstream. The flooding damage was centralized among two particular urban locations, the city of Midland and Saginaw. This virtual assessment report, both HAZUS-MH and IOA simulations were conducted to ascertain the post-disaster waste material quantities and composition.
I'll now demonstrate some of the main functionalities available within HAZUS-MH to better familiarize you with the software environment. Here you see the general HAZUS interface and ArcMap after running a damage and loss analysis for a flooding event. The first thing I will check after running a damage and loss analysis in HAZUS is the debris generation available under the Results tab. So I'll go to Results, View Current Results, okay. And we'll go down to debris. For the flooding analysis, note that a table pops up with the total tons of debris by census block. The debris composition is further categorized by finish or the non-structural debris, structural tons, and the foundation tons here. You can either copy and paste this table directly into Excel by selecting it and going to copy and paste, or you can export it as a CSV or a text file. In addition, as I mentioned earlier, you can use the HAZUS export function available here under the ARC toolbox. So here you have export, and if you double click this icon, you can then export your results. That will create an Excel file where you can actually specify what data you want to export, and it will be generated for you where you decide to save it. Let's see, notice that I can also select a column, right click it, and show export. So that's another option you have rather than just straight up copy and pasting. In addition, you can check the flood depth map here, available under your simulation here. And again, you can superimpose this flood depth map, over your debris generation results or over your census blocks as shown here. And that will let you, again, double check the reliability of the HAZUS-MH model predictions. So notice that for the flood depth map, we have high flood depths up to 43 meters in dark blue, and then low, 0 or unaffected depths in very light blue there. So the next step is I'll show you how to map the total debris quantity by spatial location. Okay, so we'll go back to results, then hit debris, and then I'll go to highlight the column for total tons, and then hit map. So that will create a new output layer here, as shown here, ABSV FR debris. And so after we do that, we'll say close, and I'll turn off the census block designation layer and the flood map as well, so we can really see what's going on with the debris generation. So you see lower debris estimates are associated with the cooler colors, so 0 to 178. And then higher debris quantity estimates are in the darker or warmer colors here, as shown. And so next thing is we might want to edit the color map. So to edit the color map, we'll right-click our layer in the table of contents here in ArcMap, and then go down to Properties. Then we'll go to General. First thing we can do is change this name to something more relevant. So we'll do debris tonnages, so total debris. And we'll select next. We'll go to symbology here. That's the next thing to change the color map. So we'll select another color map here that's more distinct. So going from blue to red, perhaps. And then next thing we want to do is select apply. So that didn't do anything there. All right, so I'll go back to this color map. There we have it. And now we want to switch the color arrangement so that red is associated with the larger debris quantities and blue is with the smaller quantities. So we go right click, format labels. And first thing we can do is change the numeric output. So we'll do number of decimal places to 0. So to clean things up. And we can do that. Notice the labels are now changed. And then we can reverse sorting. So that now we have the darker colors indicating larger debris quantity estimates. So that's pretty much, some of the ways to change the color map settings in ArcMap and using HAZUS. So we can now click apply, and now we see that the overall color map changes. We'll click OK, and there we have it. So now to print out these results, we go to View, go to Layout View. Notice that we now have, more cleaned up version what we're trying to print out. Again, we're showing the total debris tonnages generated from HAZUS. And there we have it. So we have this cookie cutter layout that now has some pre-populated values here. We have a scale to understand distances. We know north and south and west and east with the compass. We have HAZUS-MH fancy logos and other things we can actually delete, such as the overall heading here for the title, for example. I don't know why that deleted everything there. Okay, so we'll delete that title. Notice we can also update the legend, for example. So we have total debris tonnages, total tons, and we can change the font and settings of this legend by right-clicking the legend object, going to properties, and then we can go to general, and we only want to plot total debris tonnages, so we can take out all these other different layers from our legend to simplify things. Then we can go to items now and change the font, for example, to size 18. And we can also change the style. So in this case, we can go down to, something where we just have the heading and the label, something like this. Set OK and apply. And now notice we want to apply the font setting to all labels. And we can also change, the format of the legend title here. So again, usually 18 font is good to make it more legible and clean. And click OK. Notice that we now have cleaned up significantly the legend for our figure now. Now, if we want to export this figure, say to our desktop, we would go to File, Export Map, and then we would select the file type. Usually TIFF is the highest quality. Specify the file name. We have resolution, width, and height of the picture. We can also take into account. Then click Save once we've located, the right folder where we need to save the exported file, and hit Save. So that's, the ways to potentially format and present the debris generation results from HAZUS-MH for this scenario. And let's go back to data view here. So this is one way to look at the induced damage, from this flooding event. And I'm going to turn off the census block here. Now, if you're also interested in the direct economic losses of the flooding event, you can go to the results, general building stock, and then economic loss tab, and hit by fall replacement. Here you might find the total economic loss by census block that can be categorized by general occupancy class, specific occupancy class, general building type, or total overall economic losses. So say the number of dollars per census block for either building loss, content loss, and other types of expenses. So that's another helpful thing if you're looking at the economic effects of a disaster event. In addition, you can actually copy and paste, directly export or map these results. Again, if you want to map them, just select the column and hit map in the bottom, right? Additional information that might be useful when you might be performing, in addition to HAZUS, the I-waste analysis, you might want to look at the data contained within the general building stock tab under the results menu. So you go to results, general building stock, and you can select by occupancy or by, let's see here, we can also look at by building type, for example. And you can see here, these tabs include the square footages or the numbers of building material types segregated into various damage classes, say from 0 to 100%, as you can see scrolling from left to right. Essentially, these are the tables that HAZUS might use to compute the amount of debris generated for this flooding event. Again, you have the option to choose to map or export these results if interested in more specific analysis and interpretation. In addition, you can look at vehicular damage, for example, or losses generated in the community. Again, this table shows you the damages to three main vehicle categories, either cars, light trucks, or heavy trucks. So the total damaged vehicles, the total undamaged vehicles, as well as the various number of vehicles that fit in within the various damage classes, up to ranging from 0 to 100%. You can also look at the losses in terms of the economic losses, the US dollars for either of these categories, by census block and export or map these results as well. Another interesting feature in the results menu is that you can locate and assess damage to essential facilities such as medical care, emergency centers, and schools present in the disaster affected region. For example, if you go to results, essential facilities, you can migrate over to schools tab here. And here you can see the damage level of the building, of the school, the losses occurred, and the days required to reach full functionality, scrolling from left to right. So again, here is the building damage, the losses in US dollars, and then you have the days to restore that school, until it's functioning again. So you can observe similar results for medical care facilities, emergency centers, and you can also map these results spatially. So if we go back to the results tab, we can also look at utility systems, for example, and look at damages to wastewater treatment facilities. For example, in the area, there are a few that were affected in the city of Saginaw. And we can also look at oil and natural gas infrastructure. In this case, an oil refinery was affected, and look at the damage percent and the loss in US dollars. If we go back to results, we can also look at agricultural products. So if we go to Midland County, which was most affected, you can see, again, the damage to all these different crop types in the region. Another very helpful tool from an economic and social standpoint. And if you're interested in social or societal impacts from the disaster event, we can go to results shelter. And here we see the total displaced population of individuals from each census block, and those that require short-term needs as well, such as temporary housing, for example. So that's one way we can look at the social impacts from a given flooding event. We can also summarize the indirect economic losses by, say, the type of economic sector, as shown here. And that's the loss of income for each of these sectors for the given years following the disaster event. Then you also have the employment losses, say, for the different economic sectors. In this case, everything is blank because I did not choose to select this option when running the analysis in HAZUS. Remember, you have that drop down, those dialog boxes. You can either choose select all or be selective. In this case, I chose not to select indirect economic losses to make it run a little bit faster. All right, so some other things about the results tab. You can generate a detailed summary report. If you would like HAZUS to print out a nice tabular and graphical summary of the results that were generated. If you're interested in the building inventory in the region, check out all the tabs under the inventory menu here. You can query the general building stock by square footage, the building count per census block, other types of important parameters such as flood specific mapping and first floor elevations. You can also look at the total number and characteristics of the essential facilities, hazardous material facilities located in the region. For example, as I click here, that gives you the coordinates there. You can use that to update maybe a user-defined analysis section for user-defined facilities, and then look at damages to those hazardous materials facilities. You can look at the demographics of the region of interest, again, population, average rent, income, number of race and ethnicity, or other things you can look at. So these are really cool things to, if you have a lot of time available to look at, that might help in the development of these assessment reports. So that's another cool item to discover and explore in HAZUS. And you can finally check or modify the depth damage functions and the model parameters used in the debris estimation process under the analysis tab here. So by flood depth damage functions, you can look at, say, for the general building stock. This is looking at residential type infrastructure. And if you scroll from left to right, you have by depth of flooding, the different damage percentages that correspond for these different types of residential buildings. And again, whether they have a basement, other things you can check out there. Okay, so that's some of the, where you might try to find the depth or modify the depth damage functions. There's also, what else do we have here? Under analysis, the parameters here. So for debris estimation, remember I showed the table of the debris intensity, how much debris is generated per square foot of building, given the flooding depth for different types of residential or industrial or commercial infrastructure. So you can go down to commercial, for example, and look at, say, the maximum flood depth, how that corresponds to debris generation. So these are additional parameters that could be possibly changed or modified depending on, how advanced or, how much more knowledgeable you might be about the debris generation scenarios for your simulation. All right, so that does it for most of, the main functions you want to use after running a simulation in HAZUS. Notice that there's a lot of different ways you can spatially portray the results. You can display oil facilities, other types of essential facilities in the area of interest, hospitals, fire stations, and you can map different things such as total economic losses, as shown here. You can look at total debris and then also superimpose the characteristics of the disaster event. So next we'll look into the second case study.
As part of the second tutorial, we will now investigate and explore some of the HAZUS-MH results obtained from the Hurricane Laura virtual assessment report. Hurricane Laura was a Category 4 hurricane, first making landfall across the state of Louisiana on August 27, 2020. It is tied with the 1856 Last Island hurricane as the strongest hurricane to hit Louisiana in terms of wind speed. It is also tied as the 5th strongest hurricane hitting the U.S. by wind speed at landfall, while setting records for the fastest intensification rate in the Gulf of Mexico. Damage caused by Hurricane Laura in the United States was reported in the states of Louisiana, Texas, and Arkansas, with Louisiana being the most impacted, specifically the city of Lake Charles. HAZUS-MH was used to estimate the debris generated by Hurricane Laura in the 24 affected parishes in Louisiana. The HAZUS-MH analysis resulted in a total estimate of 1,239,824 tons for brick and wood debris, 64,569 tons for concrete and steel debris, and 10,788,584 tons for vegetative debris. Environmental hazards that might impact the recyclability and reuse of the disaster debris in Louisiana included the presence of plant pests and the reported oil and chemical spills caused by Hurricane Laura. The main challenges hindering improved recycling and reuse practices for disaster materials included challenging material conditions, suboptimal disaster debris management policies and planning, insufficient debris management logistics and infrastructure, and inadequate community or governmental support for recycling, as well as a lack of disaster debris data.
Here you see the general interface in ArcMap again after running a damage and loss analysis for Hurricane Laura. The first thing I would check after running a damage and loss analysis is the debris generation available under the Results tab. So go to the Results menu and select Debris. For the hurricane analysis, note that a table pops up again with the total tons of brick and wood, concrete and steel, as well as tree or vegetated debris by census block here, as the rows suggest. The debris composition is further categorized into eligible tree debris, signifying debris that might be still standing in place, but likely poses hazards or risk if not properly removed. also known as maybe trees leaning or hanging against structures, and present some types of materials or branches that need to be removed eventually. So you can either copy and paste this table directly into Excel or use the HAZUS export tool available within the ARC toolbox and ArcMap. And note that I can also select a column and right click it and go to export data, or we can select map here to show the spatial variation in debris estimates. And let's see, now we can now look at some of the characteristics of the actual hurricane event. So we'll go into results, go to storm track, and then we can now import hurricane lore storm track. So you can see it's now highlighted in black when it finishes loading here. And there it is. We can also look at the wind speeds for our region, for example. So this table is showing you the peak gust wind speed, maximum sustained wind speed for different census tracts within our disaster affected region. So all of the census tracts or blocks highlighted in orange here are, what were actually simulated during, the HAZUS simulations. So if we want to, for example, look at the wind speeds by different return periods, we can click them on and off here. This is for the 1,000 return, wind peak gust, 500 year, 200 year, 100 year, and 50 year. So you notice how the wind speed is changing with spatial location there as I click them on and off. You can also look at the roughness features. Say when you expand this, surface roughness features less than, in the range from 0.03 to 0.1 are indicated in orange, all the way up to around 1 in green. So again, higher estimates are indicating, more rural or openly vegetated areas versus, maybe more urbanized landscapes. So now we can look at some of the main functionalities available within the hurricane module to better familiarize you with some other things that you might want to look into. All right, so like we saw for the flooding event, we can look at the debris for different material types. First, we'll look at total concrete and steel debris. Notice we can, again, look at changing the color map. If we right-click this layer and select properties, wait for it to load. And then here we can change the color ramp. In this case, darker colors are indicating higher quantities of debris versus the cooler colors. We can also change, the layer name, other things that would be, good to do for presenting this in a report, for example. So that's the total concrete and steel debris. We also have the tree debris. Again, notice that different census tracts have higher quantities of tree debris versus concrete and steel debris. And that's because, again, some of these census tracts vary by, the extent of urban environments versus open and rural areas. So again, that's why there might be differences in total vegetative versus concrete and steel debris versus brick and wood debris. Again, you see that the brick and wood and the concrete and steel have pretty similar results in terms of, where the largest quantities of debris are located. Okay. So remember last time we wanted to export these results. So again, we went down to layout view, and that's where we could manipulate the properties of our legend. And then we could then export this material using file export map as a TIFF or PNG file for inclusion in a report. So if you also are interested in the direct economic losses for this hurricane event, you can go to results, general building stock, and then direct economic losses. And you can see, by occupancy, for example, you can look at, the total economic loss for all of the occupancies as shown here. And then looking at the different, types of losses, whether it's rental, income, inventory, or building structural losses, and then look at the total losses. You can also look at general occupancy classes, looking at more specific, like residential classes only, or you can go into industrial classes. Then you can get down to very specific classes. So, and that's looking at some of the direct economic impacts. You can also look at damage states, for example. Remember the probability density functions, right? The cumulative probability of some type of damage occurring. You can do that by building type, for example. And you can see here you have cumulative probabilities for different types of damage states as a function of the census tract. So again, most of these census tracts here have no high probability of no damage for a wood type building structure. You can also change that to masonry, concrete, other types of building materials. And notice there might be some differences in the probabilities as a function of the damage state. So again, that's another way to look at organizing the results. You might also look at building counts, say the number of buildings that are affected in these different damage categories as a function of census tract. That's looking at all occupancy classes. And you can look at damage to essential facilities like we saw with the flooding event, with the hurricane event. We can look at damage to medical care facilities. Again, what types of damage states they might be in, how long it might take until they're reaching full functionality after the response and recovery period. We also have other categories like schools, police stations, and fire stations to look at, describe. All right, so in addition to social or economic impacts, there's also social impacts to look at. So the primary social impact is the number of displaced households and those households that need short-term sheltering needs. So again, great for looking at response and recovery after a hurricane event, what counties or jurisdictions might be most affected and require federal, state, and local aid. All right, so like we saw last time for the flooding analysis, we can generate a summary report tab if you need a nice tabular graphical summary of the results produced. And if you're also interested in the inventory results, you can check out the general building stock, for example, the total square footage, building count, other types of important attributes that might affect how the building responds to a hurricane event, like the wind building characteristic distribution. So that's another thing you can check out. And then you might also look at the actual damage function curves, right, under your analysis menu. So for hurricanes, you can look at the damage probability functions, right? Say for this case, we're looking at a wood material building type for a single family home. We can see how the probability of a damage occurring for different peak gust wind speeds and damage states, how these curves might look. So again, remember this value is used in the actual estimation of the debris quantity and composition as output from a hurricane event. What you might also see here is the characteristics of the buildings that might further differentiate these buildings from others based on, whether there are shutters, whether it's open terrain, whether, the roof shape, the water resistance, if that's there, if there's garages. So those are other important distinguishing features that HAZUS uses in its estimation of debris generation. And then other additional things you might be interested in as far as the analysis go include some other types of debris functions, right? The debris damage intensity functions. So this is the amount of debris produced in pounds per square foot as a function of the peak gust wind speed and the surface roughness of your affected census tract or census block. Notice that under this classification, since this is a wood family home, you have masonry and wood as the main debris classification being generated for this type of housing. This will differ if, for example, we have a steel building that might, have some other type of debris associated with it. So that's just, some things you can also look into, how these damage intensity curves might change as a function of the building material type that's being classified. Then you can also look at some other parameters for debris generation, mainly looking at vegetative debris. Some census tracts differ in the predominant tree type, whether it's coniferous, mixed, or deciduous, the number of stems per acre, and the tree heights, which are important attributes for debris generation with the hurricane wind model and HAZUS. So those are kind of the most important things to look at, when after performing a HAZUS run using the hurricane module.
In this preliminary virtual training module, a standardized approach to apply FEMA's HAZUS-MH software was introduced to reliably estimate waste material quantity and composition. This virtual training module has been developed to facilitate data standardization regarding the virtual assessment reports within the SUMMEER organization and to familiarize you with the main capabilities and functionalities that HAZUS-MH can offer, focusing specifically on post-disaster waste materials estimation. I have also highlighted some important additional capabilities available within HAZUS-MH for quantifying economic and social impacts of disaster events, such as human injuries or casualties, financial losses, and damage to critical infrastructure such as transportation networks, utility systems, or waste management infrastructure. That concludes our virtual training module for today. Thank you for joining our presentation. We welcome any and all feedback for improvement. If you have a specific question, please be sure to contact our organization via one of the options below. I've also included my personal email below should any specific questions arise. Thank you again and take care.